Hi, welcome. So, in the introduction videos, I have already discussed that what are the important topic related to your solid mechanics, and here uh, in this video, I will specially discuss the introduction of stress and your strain. Okay, so let's start. Before starting your stress and strain, I think you need to learn what is elasticity. Okay, so before learning elasticity, you need to do some assumption. Let's assume any particular material or body shape. Okay, so what is assumed that this body consists of a numerous of particle or molecule, and what happens when you apply any load? Simply the distance between this molecule get increased. Okay, or you can say this particular fiber within this body get strained. Okay, and more logically or more technically, if you transfer this force and if you transfer this force into work, you can express that the increment is delta. So external work is your p delta. So this external work converted into internal potential strain energy. Okay, potential strain energy, and due to the strain energy, this fiber stressed and it is hold as a, or it is stored as a form of potential energy. Just for this reason, when you remove this force, again it will come back to its original shape, or you can say this potential strain energy again converted into external work. How? Because it has again shortened by amount of delta. So what is elasticity? Elasticity, you can say, this is a property. This is a property of any material to regain its shape. When it's regain its shape, when the load which was applied on it is removed. So this is known as the elasticity of material. You can visualize this elasticity very well if you take a spring, for example. Okay, take any spring, this is supported here, and then you apply a load. What will happen? This will simply stressed. Okay, now again you remove this load. What will happen? It will come back to its original shape. So this is happening due to the property which is known as your elasticity. Okay, now elasticity can be perfect or partly. What happened in case of perfect elasticity? In case of perfect elasticity, the shape or the original shape is again regained after removing of the load. But in case of partly elasticity, this increment remain. So in this case, you can say after removing the load, the final shape is like this. So a permanent settlement has remained. Okay, you can say it delta dash, and you can now say why this is happening. This is happening, again go back to the physics. Here what happens after removing this load, the potential strain energy again was converted into external work. That's why it was come back to its original position. But in case of your partly elastic material, what happened? Some amount of this external work converted into your heat. Okay, that's why it cannot come back to its original shape. A permanent a permanent deflection here, sorry, it was wrong, a permanent deflection here remain. Okay, clear? So this is all about your elasticity. Now related to this elasticity, there is some theory. What are the theory? From different type of experiment, it has been observed that when you apply load on a body, the stretch or increment in length is proportional to your load. So you can say this deflection is proportional to the load. Okay, and further this phenomenon was experimented by Mr. Robert Hooke. I think you have heard of this name. And he says that not only this increment in length is related to your load, rather it is dependent on like this. It is proportional to your load, proportional to the length of the material or the body, proportional, inversely proportional, not proportional, it was inversely proportional to the cross section of the body and inversely proportional to the property of the material. Let's say it is E. I will discuss later what is E. So if you combine the theories says by Mr. Hooke, it comes like that: the deflection under any load on a material or body whose length is L and cross sectional area is A. In that case, deflection is PL by AE. I am just simply combining all this relation. So this is the Hooke's law, or the deflection can be expressed by this formula. A million tons of questions may come, whether it is GATE or EAC, from this formula only. Okay, you can check the previous year questions, and from there you will get a lots of questions are asked simply based on this formula or the Hooke's formula. What? They simply give you the length of the body or the cross sectional area of the body or the uh, elasticity or this material property, and they ask you about the deflection, or sometimes they ask about the required load for particular amount of deflection. Whatever, maybe it is asked that how the deflection and cross sectional are varied. You know that they simply varies inversely. Or they may ask that when cross sectional area is increased by twice or decreased by twice, what about the deflection? This type of questions, which are thousand in number, if you check out the previous year question, you will get that thousand of number of questions are asked simply from this Hooke's law. Okay, so this is all about the Hooke's law. Now we will discuss about the implication of this Hooke's law. Why? Again, let's see what happens from this Hooke's law. Okay, so it is clear to you that Hooke's law says that deflection is nothing but your PL divided by A. Okay, this is our base formula. From this formula we'll derive some other relation. Okay, so come back to your equilibrium. Let's say this is the body, you are applying your load. What will happen? You know, due to this applied tensile load, all the fibers are stretched equally. So internally, if you cut any section, let's say here, you will see that due to this uniform stretch of each fiber, due to this external load P, there is an internal force is developing within this cross section. Okay, so let's say the magnitude of this internal force is sigma, and sigma is nothing but load intensity. Load intensity means simply force per unit area. Okay, so from equilibrium, if this part of the body have to stay in equilibrium or in less or motionless, what should be happen? This external force should be equal to the summation of this internal force. No doubt. Okay, so this each force is sigma. Okay, so for entire cross section, what is the total load? You know that sigma is the load per unit area. So for entire cross section, the total load is nothing but sigma multiplied with your cross sectional area. So from here you get that external load P is nothing but this load intensity into cross sectional area, or you can say sigma is equal to P by A. Do you know what is this? This is known as your stress. So what is stress? Stress is load per unit area. Again, lots of question may ask from this formula. A very simple formula, but lots of tricky question may be asked from this formula. This is all about stress. Now again, consider this figure. Okay, so after applying this load, what happened? It was simply stretched. Okay, so total amount of stretch, let's say it was delta. So if the length was L and total stretch or total increment in length is delta or small delta, let's consider small delta. So I can say for length L it was increased by length delta. For unit length it was increased by delta by L. And this increment for unit length is known as your strain. Clear? So you have learned what is stress. Okay, now you have learned what is strain. Let's combine the stress and strain in your Hooke's formula. Let's see what happened. Okay, so what was our Hooke's formula? Delta is equal to PL by A. We have learned stress is equal to P by A. P by A. And also we have learned that strain, let's denote your strain by epsilon. Strain is equal to small delta by L, or deflection or increment in length due to unit length. Okay, so simplify this formula. Delta, just bring down L here. Delta by L is equal to P by A is already there. Separate it from E. Okay. Sorry for the intervention. So we have got your increment for unit length, and let remain P by A as it is, and separate 1 by E. Now replace this delta by L by your strain. So strain is equal to, you know, P by A is stress divided by your 1 by E. So you can say from Hooke's law we can write that our stress is equal to epsilon into modulus of elasticity. Don't call it modulus of elasticity now, just a material property. Or you can say your stress related to strain, or stress relation is simply follow the linear model. Okay, so if you put this stress strain relation, it should follow this straight line, where this is your strain axis, this is your stress, and the slope is nothing but your stress by strain, and this is, from this equation, is E. So this E is the slope of the stress strain diagram, and also known the material property or modulus of elasticity. Okay, so in many examination question, the stress is given, strain is given, or the material property is given, stress is given. You need to ask for finding this strain value. So we have covered already what is your elasticity, what is your Hooke's law, the implication of this Hooke's law. Now it's time for discussing what is stress strain diagram. Okay, don't worry, after discussing this stress strain diagram we will complete or stop the lesson for today. So what is stress strain diagram? First, learning the stress strain diagram, you should ask yourself, okay, that why we should learn stress strain diagram. What is the implication? As an engineer you should know the safe stress. Okay, what is the safe stress of any material, and only in that time you can use that material for your engineering purpose. So to know this safe stress, you need to learn, or you need to listen a story. Okay, so just now we have discussed that your stress simply follow the linear relation with your strain, or you can draw this like this. But this relation valid for certain limit. If the stress value is very low, okay, or the load remain within certain limit, only in that time this follow this stress strain profile as linear. Okay, after that it become complicated like this. Okay, so as an engineer we always should stay within this zone. Why? Because this is the elastic limit where stress is proportional to your strain, or we can say if we remove the load, okay, our material regain its shape. There is no permanent deformation. But if you exceed this limit, okay, if you exceed this limit, let's say here, in that case it is behave or it behave like a partly elastic material, and in that case there always remain a permanent deflection within your member. It is not at all desirable. That's why we need to find out this limit, or the limit of proportionality. Limit of proportionality. Okay, this is very much important, or we can say this is sigma L or sigma P. Let's say sigma P. Okay, so limit of proportionality. In real life, this is very difficult to find this limit of proportionality. Okay, so when you test any body, let's say this is a steel material, you are testing this under tensile load. What will happen? Well, if you follow the stress strain diagram, it looks like this. Up to a certain limit, it goes linear, then it become curve, then without application any load, it simply what should I say, simply stretch infinitely without any increment in stretch. Then again it gets its strength and reach a maximum point, then it collapse. So what are the salient point here? This is the point, you know, this is the limit of proportionality. This is another point where without application any load, your material simply stretch. So very dangerous for our structural material. Without application any load, if it stretch, this is not at all desirable. Then again this material gains strength and reach a maximum point, then it collapse. So let's discuss what are the each point. This is known to you, limit of proportionality. This point is known as starting of yield point. Yield point. Okay, what is yield point? At yield point, without increment any load, your material stretch. So this is not at all desirable. I am not applying any load, but still my material is deflecting. Okay, this cannot be happen, or this even it is happen, it is not acceptable. Now next is, this is the end of yield point. Again it gain its strength. This stage is known as your strain hardening. Okay, now you may ask me why it is happening. Here it has already failed, one type of failure. Without applying any load, my material has stretched, that means it has failed. So why again it is gaining strength, and why it is known as strain hardening? What happened after yielding of the material? Again this molecule or particle get rearranged. Okay, and due to this rearrange, say they again acquire some strength. That's why it is known as your strain hardening. Clear? Due to this strain hardening, they reach to a maximum level of point, and this is known your ultimate strength, not stress. Okay, ultimate strength. Why? This is the limit, and this maximum limit is known as your strength. Below this strength, if you take this stress corresponding to this strength, this is the limit of stress. Below this stress limit, every point is known as your stress. Okay, and this is your strength. So strength is your ultimate, that's why it is strength. And what about this point? This is known your collapse point. So you need to find this limit of proportionality, but you have yield point and the ultimate strength. To find this limit of proportionality, a very sophisticated instrument is used, and the value of that instrument and the value of this limit of proportionality stress is directly related to the sensitivity of the instrument. And it is very difficult to find this particular value, but we need to know this value or the stress corresponding to your proportionality, limit of proportionality. So what we do, we don't to eliminate all the difficulties, we don't rely on the instrument, we simply test it. Okay, during test we know after this point it curved, then yield come, then strain hardening come, then ultimate point reach, then it collapse. Clear? So this is observable, this is also observable. Let's say this is your stress corresponding to yield point, or let's say this is strength corresponding to your ultimate stress. So to find this our working stress in this zone, this is our working zone below this limit of proportionality. What we say, this is working zone. So sigma, to find sigma working or safe, we simply divide this yield point by a factor, or this ultimate strength by a factor. And what is this factor is known? You know, this is known as your factor of safety. So you have learned what is stress strain diagram, but it is not only important to learn what is stress strain diagram, what are the salient features, what each point known, what is the name of this part. Everywhere you will get the answer, whatever textbook maybe it is, whatever the study material you are following. But you should learn why you need to know this stress strain diagram, what is the implication in your engineering life, or why it has been asked in the examination. The reason is this: you need to find this working stress, and it is not possible to find this working stress by your measurement. It is not impossible, but it is difficult. To eliminate the difficulty, you are relying on the yield point or the ultimate point, because these are visible point. Okay, so that's all for now. Again, in the next video, that means tomorrow, we'll discuss about maybe the strength of material or about any other topics of other subject. Okay, so till then, please study and try to solve the questions which have come in the previous year, whether it is in GATE examination or ESE examination. And if you have any doubt, if you have any difficulty to solve any problem, please don't hesitate, let me know in the comment section. Definitely I will try my best. I am again saying that I am not an expert in teaching, but as the current scenario is worsening for many students who are physically weak, who cannot afford your coaching online or offline, whatever it is, for them this is my slightest, you can say, I'm trying my best to make them benefited. That's all. So till then, bye.